So I want to take this idea of spectrum and apply it a little bit and see how it helps us learn more about the universe that we live in. So today we're going to define the Doppler effect, and we're going to describe how it occurs in the natural world, and then we're going to determine whether an object is moving towards or away from an observer. Have you ever been standing on the street and heard a siren go by? You hear that sound coming towards you and it changes, right? So as it gets closer and closer and closer to you, that sound changes to a higher pitch. And then after that siren passes you, it changes to a lower pitch. So as the sound waves are coming towards you and then moving away from you, they have a different sound. So imagine a little bug on the water, and he's just sitting there doing his little bug things. And he's kind of bored because he's just sitting in the water. So he starts wiggling his legs. And as he does so, he creates patterns in the water. He creates those waves disturbing the water. He's doing it at a constant rate. And so if you are standing over by A, you have this certain frequency of waves that are coming towards you. If you're standing over on B, you have the same frequency of waves coming towards you. So then say the bug starts to move to the right. He's still moving his legs, so he's still creating those wave patterns. And let's just assume he's still doing it at a consistent rate. Right? So where he was standing still and the frequency was the same all around him, now he's moving to the right and the frequencies are going to change a little bit. So if you're observer A over here on the left, each crest has to travel further than the one ahead of it because the bug is moving to the right. So he's spitting these waves out, but because of his motion, the waves are more distant between them. Sounded weird. On the right, observer B would have a higher frequency of waves. So they're arriving more frequently because as he's spitting them out, he's still moving to the right. They're coming more frequently. So as the observer on the left looks, the frequency of the waves decrease because there's more space between them. The observer over here at B is going to have an increased frequency because it looks like there's less space in between them. So let's review our electromagnetic spectrum real quick. As we go to the left, the frequency is higher. Notice in our visible light, to the left and the higher frequency is the blue end of our visible spectrum. What happens if you go to the right? Our frequency decreases. So as we move to the red color of our visible light spectrum, our frequency is lower. So think about our bug. Which side was the lower frequency? The lower frequency was the side where it was moving away from us. The higher frequency was the side where the bug was moving towards us. So let's look at this in terms of spectrums. Say this is a mixture of gases that we're looking at in the laboratory. We have these absorption spectrums, so you can see those black lines that show which gases we have in our sample. And this is the sample at rest. If we take that sample and we move it away from us, the spectrum will shift to the red. It's going to shift to the side with a lower frequency. So it's the same lines, just shifted a little bit to the red side. Based on this, we can say that if we have, say we look at a star or a galaxy and we see hydrogen in it, we see those hydrogen lines, but they're shifted just a little bit from where we would expect them to be if they were at rest in our laboratory. That would let us say that that particular object is moving away from us. Now, if we take that same sample and move it towards us, the frequency lines move a little bit to the blue. Remember, the blue is going to be a higher frequency. So higher frequency is where the bug was moving towards us. So an object moving towards us will have a blue shift in its spectrum. So let's look at this in terms of a spectrum from a galaxy. So here we have our hydrogen lines, and this is a laboratory reference. So this is something that they took into a dark closet and they looked at through a spectroscope and decided that here's where these lines for hydrogen define whether or not we have hydrogen in it. Let's compare this to a nearby galaxy. It's pretty close to us, and if you notice, it has a lot of spectrum lines. There's a lot of gases, there's a lot of things inside of a galaxy. So when we see a spectrum of a galaxy, we're going to have a lot of things to deal with. But we're really focused on those hydrogen lines. So those hydrogen lines aren't exactly where we would expect them. They're shifted a little bit to the right, which is in the red side. Remember, the red side is going to have a lower frequency, and so that's going to mean that that galaxy is moving away from us. Now, what if we look at a little bit further? So a little bit further, those hydrogen lines really aren't anywhere near where we would think they would be. They've shifted a lot. So this particular galaxy has shifted a lot more into the red. So the waves are coming much less frequency. So that must mean that it's moving away from us at a faster rate. And then if we look at this one, those lines, they don't even look like they're in the same color. So what's happened is those particular galaxies, everything in that galaxy is moving away from us very, very quickly. And so it's shifted much more into the red, so it's moving much faster. This is what we call redshift. So the Doppler effect is that idea that those waves change their frequency based on whether the source is moving towards or away from our observer. The Doppler effect occurs in sound and it occurs in light. Those are the most common ways that we see it. And it can be used to determine whether an object is moving towards or away from our observers.